So I'm Junli Gu. I'm the tech lead of Tesla for machine learning. But we cannot talk on behalf of Tesla about Tesla project or Tesla roadmap. So today instead, I'll focus on the technical summary of this whole domain to my personal understanding. So my viewpoints does not represent anything from Tesla today. Thank you. Which I think is good. So we've already have the expert from Google, and we will have the expert from Baidu talk about their product. So we do need once in a while somebody summarize based on the matter of facts, the technology, where we are, what do we need, and the existing challenges. So before I joined Tesla, I'm not actually an expert on the cars. So before I joined, I took a serious study on the vehicle revolution. So I will share that as well. I believe a lot of audience here today are not necessarily from traditional car companies, but we are here together to solve the problem. And then the challenges, technical challenges, I summarize it. It is like one sentence: when big data meets machine learning in the car itself. So it's a very specific user scenario. It has its very crucial challenges from our domains. And I will dig into that. This will be the majority of my talk. And then I will conclude. So transportation evolution history. It's not necessarily a beautiful picture, but it summarizes what I want to say. So from 1900s, we have cars. That's when human jumped from horses into vehicles. And that history has been evolved for another hundreds of years in keep improving the mechanical technologies, keep improving especially the motors, and make the car drive fast, make the car beautiful, and nowadays make the car all colors and different little technology to differentiate each car company. But now we are something big. About 10 years ago, there are companies in this domain pioneers a revolution in making the mechanical parts into digitalization. So one of the big pioneers, of course, is Tesla. I do really admire the innovation spirits of Tesla. It makes all the car components a digital device. So it's visible to the digital world, so to the computer. And now, of course, we're talking about ADAS system. Not only want to control the car in a smart way, but we want the car to drive itself. That's the biggest challenge right now. And it's a big change of digitalization. And then eventually, I believe everybody is talking about making the car intelligent enough. So the car can drive in the world like we do. I don't know exactly how many years it will take to get there, but I do believe those are the essential steps that the car needs to go through in order to be able to get there. So a revolution from analog to digital and then to intelligence is 3 steps in the vehicle revolution. So first of all parts need to become digital controllable in order for the car to be intelligent enough. Not everybody realizes like this is an important step, but this is a fundamental step. And then we will have complex sensor systems to sense the world. Like different types of sensing technologies will be used and still need a lot of space to improve in order to collect the accurate information we need. And then driving through perception. So we have the data, we have the controllable devices, and now it's about the build up the technology, which means majority of the algorithm, and then the computing to make sure that we can perceive the world and the car can drive based on the perception. Eventually, of course, everything will be deployed through the computing, which means the computer will be the fundamental enabler to this technology and this trend. And the car eventually will become agent with autonomous driving behaviors, positive industry impact, and maybe potentially some negative impact on human life as well. So that's another topic to discuss. So there are a lot of discussions in this trend, in this direction. I believe, my personal belief is everybody pretty much share the similar opinions from DARPA challenge in robotics and in self-driving cars as well, in the basic key components like shown in this figure. which, so first of all, have a sensors. You see all kinds of sensing systems. The sensors functionality is to collect the data as much as we can, of course, 360. And then we'll build through different kind of algorithms, the perception system. And this perception model will be integrated together with GPS mapping and localization algorithms to provide a 3D, 360 accurate world model. And then path planning will based on this. And then based on where we are going to design path, now we go forward, we turn left, such things. And then all this command will be passed to the control system to control the car. So this is a loop. And this loop takes the input from the real world and take the real effects in real world. That's the difference of this AI application. So I believe last year there are a lot of discussions on the sensor systems. Like a lot of people ask, what kind of sensor is the sensor? The answer is no sensor is the sensor, only sensor system. Hybrid system is the sensor. So a sensor system these days, I believe from the major self-driving cars you can see, they use like a mixed, like camera, radar, and LiDAR. I don't think any company is using a single sensor system these days. And sensor technology is the key, but it's not there yet. In both the single sensor itself needs to keep improving on a lot of the sense, for example, camera in the dark, camera in different situations, and the sensor fusion algorithms is not exactly there yet. And then today, most sensor data are not like fused exactly the way we want, so that's another technical challenge we need to solve. So in the end, I would say the sensor system you use depends on what kind of data your algorithm needs. And then again, depends on what kind of objects you wanted to understand around the car. So it's decided by the functionality of the self-driving, not by just pure technology or preference. A case study. So it's great. We just have a Google talk. Google self-driving car, of course, starts from high resolution laser. And this is an example I could search online. So radar information is great, very accurate and fast in capture the moving objects, distance, the speed. But it may be a little challenging to understand the semantics, the rich semantics of the objects, for example, the size, and then the objects giving the same size, the moving at the same speed, and how do you differentiate them, like what kind of object there is. And the camera data on the other side has very rich semantics information, texture, material, colors, traffic lights. So for example, on the right, we can see all different things. That's what we see from the human eye point of view, the information. And again, you can see those are different sensors, completely different information that decides on, again, how you build the algorithm. For example, using radar information to build the perception algorithm will be very different from using camera data to build the algorithm. And they also will mean they have different amount of computing requirements. Also will mean that when you deploy them, you will have a different kind of hardware requirement. That's about the general introduction about this vehicle and transportation revolution as to my understanding, to give an overall picture. Again, this revolution is so huge, it has such potential impact on industry and human life. That's why so many experts are like using all we know from the information theory, all we learn from school, all we learn from industry to solve this. And my personal opinion is machine learning will be the major algorithm and will be the major theory to help us to get there. So that's why I will spend most of this time to talk about the key machine learning subdirections that I think are useful and are interesting. If you're interested in solving this domain to understand it further of where we are. So when we use the sensor data and we try to build a modeling of this world, which is called perception. And there are the first three key components we wanted to understand. So first, what is around us in objects? And then where, exactly which direction that is. And that's not enough. We wanted to understand the extent of each object. For example, this is a car. How big is this car from the front to back, from left to right, so I don't run into it? And that poses like pixel level segmentation or very detailed, accurate understanding. One of these challenges to build. And then policy. Suppose you understand everything, so what do? You want to be aggressive, you want to get there fast no matter what, or you want to be safe. And so this is another thing to really understand, which I think reinforcement learning is very interesting there. And of course, end-to-end learning is a beautiful piece of concept, and people wanted to really understand that. So talk about perception, we really have to give big credit to the DNN success. In late 2012, AlexNet broke the records of ImageNet competition to by very big gap. And people see the big potential in technology sense of what we can do by computers and big data. Then this trend has been improving to recognize 2D objects from images and from real-world images, not like well-labeled, aligned-centered images. So DNN basically is we use a very complex DNN model, has millions or billions of parameters, and then we train based on again millions, sometimes billions of data samples. So this algorithm can like convert to a state it can recognize thousands of objects very reliably. By reliable, I mean it's a statistic matter. Right now, I think the best DNN algorithm can recognize large-scale objects at 98% accuracy. This is higher than human expert. By human expert, I mean somebody who is trained to recognize different objects can do 95%. So to some extent, like computers can recognize objects very reliably. That gives us a big hope. That's, I guess, most people are starting from. And then, but that's 2D. And the world is not flat. It's 3D. And it's changing every minute. So we need depth information, and it's critical to control the driving and the speed, the speed, where you want to accelerate, where you want to slow down. So depth information is very important. And then, so of course, we talk about radar. Radar is very good in depth information, but the sensor fusion technology is not exactly there yet. So some other people will use RGBD depth cameras. So it's kind of a fast evolving technology here, which we don't have like a major technology like DNN to get there right now. So that's a challenge. And in order to understand what you see 360 every pixel, what object it is, especially the objects that are key to driving, for example, pedestrians, cyclists, and other vehicles. So then this will require a far more challenge than just to recognize what object that is. So segmentation, pixel level dense segmentation will give us advanced understanding of each pixel and how to avoid running into anything. Eventually, I think it's very interesting if we combine the 3D model with depth information to the segmentation. So we basically have a 3D world segmentation understanding and modeling of this perception. And only by that time we can kind of have a feature mapped functionality with human eyes. So, and again, we really have to appreciate how human bodies have advanced features. When we say camera all have the same functionality of human eye, no, they don't. They're far from there yet. So that's why the algorithm needs to be really evolved in our sense based on sensor data to get there. So eventually we will talk about policy. Right now, not a lot of people talk about policy because we're still, struggling with all kinds of perception algorithms or data. So my personal vision is in the future, not only will we have self-driving cars, but we'll have different personalities of self-driving cars. For example, aggressive ones. For example, like you just want to get there ones. For example, safe ones. And that personality can be associated to the driver or the owner of the vehicle itself to make it more fun to the driving experiences of the car. So reinforcement learning is basically given that we are understanding the world at any, say, arbitrary states. And we wanted to have a policy that will help us to get there based on the goal. For example, for the Go game is about get there, of course, win. For the drive, it's giving safety, get there the fastest as possible. End-to-end learning is a beautiful concept, and it's also a beautiful hope, like how we can use machine learning to get from the raw input from the sensor to the control itself without even understanding the key steps. Just say we don't want to even understand. Suppose it's a black box, I just want to get there. And I really like the concept, but right now there are certain challenges. As I said, machine learning is data-driven. Unless you have the data for each step, and then you can say, oh, now the algorithm can train itself. If you don't have the data, and you don't even can break down the data into different steps, then that's a key gap for the algorithm to develop. Very quickly, I want to really touch the other key challenges in the car. Often people will forget. Often people will just focus on one area and say, we just want to build the algorithms. But there are key challenges. First, the system, the computing system is eventually the final enabler. A lot of times people build such complex algorithms, there is no hope to deploy in a real car that will look like a normal car. But eventually, self-driving car will have to look like a normal car. And it's not easy. For example, control will use some like x86 or ARM processing, and the camera data will for sure use data parallel computing formats, for example, GPU. And people like Mobileye and Google are even building accelerators because they foresee the challenges of the system. And the cloud-based solution is agent plus system. Suppose the agent is not powerful enough to do all the computing, we want to rely on cloud. There are companies definitely proposing ideas and technologies based on that, but the reliability and the real-time response is going to be the key. Vehicle to everything, I think is a fun concept to play with. And then don't forget interconnect within the vehicle itself. It's high volumes of data exchange among the sensor system to the corresponding computing components and to the control. And so interconnect has to be high speed, has to be reliable. So conclusion, cars, my personal understanding, cars are transforming from analog device to digitalization and eventually to intelligence. So all the key steps play its own fundamental role to enable the final goal. The key challenges are summarized as when big data meets machine learning in the car. The big data are provided by the sensor system, not a single sensor. A sensor system, hybrid sensor system, that real-time 360. So the machine learning algorithm is the key to build the perception of this world in 360, in 3D model, in pixel level. And then computing in the car, don't forget computing. Computing has a hard envelope. When you build a hardware system, you cannot go beyond what the transistors provide you. That's a hard requirement that I would suggest everybody keep in mind from the day one when you design the system if you're serious in developing the cars. And then cars will be connected both externally and internally for the computing and for everything. So to summarize my talk, I know it's definitely exciting. It's an exciting industry. It has huge impact. And people jump up and down from the scare to the great hope to get there in 1 year, get there 10 years. But I would guess we really need to sit down and solve the technical challenges from information theory, from the vehicle, from mechanical, from control, from computing. So whoever will address the technical challenge will harvest the influence. Thank you very much. It's an honor talking here.